Okay, I'm going to go over number 65 from the textbook. Here is the problem. You have a mass of 4 kilograms and another mass that's on the ground of 2 kilograms. And the problem is that you want to find the time it takes for this to hit the ground. They both start from rest. So obviously this is going to accelerate this way. The pulley itself is accelerating. Okay. So again, if when the pulley is accelerating and it's rotating, that means the two tensions here and here are not going to be equal. Now, if the pulley was fixed and it wasn't rotating, then these two tensions would be equal. But in rotation, that's not the case. So here are your free body diagrams. You have mass 1, mass 2, and the pulley. Mass 1 is accelerating down. So you have the force of gravity and Ft1. The force of gravity is bigger because it's accelerating downward. Mass 2 is accelerating upward. So you have Ft2 and m2g. And then you have the pulley. So the pulley has all these forces on it. So in the pulley, you have an axle, okay? And that's where we're going to consider the force of gravity of the pulley. The pulley has a mass, so that means it has a force of gravity. So this is the mass of the pulley times gravity. You also have Ft1 that's pulling down on the pulley. You have Ft2 that's pulling down this way on the pulley. And then you also have the frictional torque, which the problem tells you about. Let's see what they say about it. So, textbook problem 65. Okay. The friction at the axle exerts a torque of magnitude 0.5. Okay, so that's right here. So, whenever we have friction, it always opposes the motion. So, this also is true about frictional torque. So, I'm going to go back to the problem. So if this is accelerating this way, that means my frictional torque, I'm going to draw right here, that's my friction. Okay, I do want to point out one more thing here. I have 3 forces pointing down. Now this pulley is not, it's not moving up or down, so this thing's at rest. So that means there's got to be a 4th force pointing upward. And that's the normal force. This normal force is going to be equal to the sum of these 3 forces. Okay? This will become very important in the AP question I posted that's due Monday. So you'll need to know this. This is like the same exact problem almost in terms of the free body minus the friction. Okay, so we're going to write down our Newton's laws equations. So I have the net force of 1. So that's mass 1 times the acceleration. Acceleration is going positive this way, so this is the positive force. m1g minus ft1. Okay? Net force of 2, which is m2 times a, and that equals, this is the positive direction, so this is the positive force, ft2 minus m2g. And then I am going to do the pulley. Net torque equals I alpha. And again, it's accelerating this way, counterclockwise, so that is my positive direction in this problem. So Ft1 times R minus Ft2 times R. And then friction opposes the general acceleration, so minus the torque of friction. And they gave you this number. Okay, so I'm going to plug everything I know into this, but first I'm going to solve for Ft1. So Ft1 equals m1g minus m1a. Ft2, I'm just isolating the Ft here and the Ft here. Ft2 equals m2a plus m2g. Okay. And I'm going to plug this in for this. Now I'm going to plug this in for this. And I'm going to figure out what I is based on some variables. So I'm going to start a new page of this. Okay, so my net torque. I is, this is the cylinder or a solid disc. So I is 1/2 mass of the pulley times r squared. And alpha is a over r. And that equals ft1, which I'm going to sub that in. It's m1g. And I'm going to distribute the r2 right now times r minus m1a times r. Okay? And I'm going to subtract it. This is ft2 times r. So again, I want to distribute the r. So minus m2ar plus m2gr. And then minus my frictional torque, which is 0.5. Okay, and while I'm distributing stuff, I'm going to distribute this minus sign. So I'm going to put that here and here. Okay, so I can get rid of these parentheses actually, if I wanted to. Okay, so I'm going to cancel out everything I can. So I can cancel out one of these r's. And in problem 6 on page 20, I was able to cancel out the other r with this, but I'm unable to do that in this problem because it's not in every term. There's no r in this term, so I need to keep this r. It doesn't cancel out. So make sure when you cancel stuff out, everything's in that variable is in all the terms. And in this case, it's not. Okay, so I'm going to have 1/2 mass of the pulley times r times a equals m1g times r minus m1a times r minus m2a times r minus m2g times r minus 0.5. Okay, then I'm going to take all my terms with a and put it on this side. So that is this term and this term. So I'm going to add that to these sides here. So on my left side, I'm going to have 1/2 MPRA plus M1AR plus M2AR equals M1G times R minus M2G times R minus 0.5. Then I'm going to factor out the A, 1/2 MPR plus M1R plus M2R equals this side. Then I'm going to solve for A, plug everything in, and I get 1.6 meters per second squared. I'm not done yet, though, because I'm looking for time. So now I can start my kinematics, which is actually the easiest part of this problem. Here are my knowns. Here's my unknown. My known is delta y equals -1 meter. My acceleration is 1.6. I just found that. My initial velocity of the blocks is 0, and I'm looking for time. So I'm going to use this equation. Delta y equals v naught t plus 1/2 at squared. This is 0. So t I'm going to solve for, and I get 1.1 seconds. Here's your answer. Okay, I'm going to wrap this video up with number 7 on this page. This is page 21. Okay, a 0.31 kilogram cart on a horizontal air track is attached to a spring. It says spring, but I think on yours it says string. Okay, attached to a string that passes over a disc-shaped pulley, etc. And it's pulled an applied force of 1.1. Okay, so this is a force of 1.1 right here. Draw a free body diagram of the pulley and the cart. I'm going to start with the cart because I think it's easier. Whenever they say something like air track, I don't know if this problem says that there's no friction, but this type of statement implies that there's no friction. Frictionless. It's like an air hockey table where there's minimal friction. Okay, so for the cart, you have this tension force, Ft. And then you have force of gravity of the cart. I'm going to call it M1G, and the normal force. Okay, and this thing is accelerating to the left. Again, no friction. And then with the pulley, this is the pulley right here. I don't know why I'm doing this here. I'm going to do it actually over here. Pulley. Okay, so you have force of gravity of the pulley, force of gravity of pulley, the normal force of the axle. We have Ft, and then we have this applied force. It's pulling this thing down. So I'm going to call it applied force. Actually, I'm just going to call it 1.1 newtons. Okay. Actually, I made a mistake here. So let's think about this. So this pulley is not moving in any direction whatsoever. It's not accelerating. So the total acceleration of the pulley in the x and the y direction is 0. So ax equals 0, ay equals 0. So that means all the forces need to cancel out. They need to be in equilibrium. So if my normal force was going up, like I have shown, that would mean that the y direction could potentially be in equilibrium if this is equal to the sum of these two forces. But my tension force doesn't have a force that's pulling it this way. So that means that this normal force is actually going to be angled because it has to have an x component. So normal force x, and it has to have a y component, normal force y, for this to be balanced with this, and this to be balanced with the sum of these two. Okay, so I'm going to call this my normal force. Okay, so that's actually, we haven't really talked about anything that looks like this at this point. Okay, find the tension in the string between the pulley and the cart. So I'm looking for this tension, and then I'm looking for the acceleration. So let's write some Newton's second law equations. So this is the net force of the cart, and that equals M1 times A. And the forces that are pulling it is just the Ft. Okay, I don't have friction. And then my net torque equation is I alpha. And so the only forces that are causing, I'm going to erase my components of my normal force here. I have to redraw this. Okay. So the normal force doesn't cause a torque because it's coming from the center. The force of gravity doesn't cause a torque because it's coming from the center. So the only two forces that are causing the torque are the applied force and the tension. Okay, so, and again, this is accelerating this way. So that means my applied force times R minus Ft times R. There's no friction in this like that was in the last problem, is equal to I times alpha. Okay, so